All right. So D is going to be the depth to the centroid of the reinforcing bars. And AS is going to be the total cross-section area of all the rebars at EM the tension side. It means that some incident you're going to see here, some compression rebars we're going to put here on the top. This total cross-section area, we're going to call it AS prime. So it's not going to be the same as AS. You cannot add it to it. So when it comes to AS, it's going to be only the rebars in the tension side. Now, how do you know that the concrete is cracking? Code is giving us an equation. It says concrete is going to be cracking the tension side when the stresses is going to be approaching 7.5 square root of F prime C. And if you recall, as I indicated before, this is a PSI code, which means F prime C, it needs to be in pound per square inch. Like, for example, 4,000 PSI, 2,500 PSI, 5,000 PSI. Don't use this equation here in KSI and then divide the whole thing here by 1,000. It's not going to work. So I want you here to imagine that you have a beam that you start to load, simply supported beam, very simple beam. You start with the loads. And you're going to be doing here incremental load, which means that you start with just the self weight of the beam, and then you start to add some loads to it as you go. At the beginning, the stresses top and bottom is going to be very small. It's going to be lower than this limit. So this is like a limit. What does it mean by limit? It means when the stresses in the tension side only is going to be reaching this value, you're going to see some cracks at the bottom, some good cracks. So at the beginning, you just have the self weight, and then you start to add some loads to it. Now the stress is going to be growing up. It's going to start as very low value, which is going to be lower than this. And as you add more loads to it, the stress is going to be growing up, the bottom, the top, and they're going to be the same in a rectangular section. Tension, compression, they're going to be equal as long as you are within the cracking limit. Once you hit the cracking stress at the bottom, what's going to happen now? The bottom of the beam is going to crack, and the beam depth itself is going to shrink. Let me take you here back one slide. Just imagine here, at the bottom, the crack is going to happen. So what happens here to the total depth? It's going to get smaller because the concrete here is not going to be good. If the concrete is going to be cracking in tension, it means it is not effective anymore. So the beam depth is going to get smaller. It doesn't mean that the beam depth itself or the beam is going to get smaller physically, but with regards to analysis, the beam depth itself is going to be smaller than what you think. So let's say the crack depth here is going to be an inch. This means this edge, the effective edge that you can use in your analysis, is going to be reduced by 1 inch. Why? Because it is not working anymore, the bottom inch of it. This is the reason that you are going to be adding this reinforcing. Why? Because at a certain point, the crack is going to be growing, and now you would like, what you'd like to do here is to have these rebars to resist the tension. It doesn't mean that the crack is going to stop, but it means that the rebar is going to be starting to take in some tension force. The crack depth is going to be growing up to a certain point as long as you add loads. And also the reinforcing bar is going to be taking the tension force that you want it to take. Here's the stress distribution. If the beam is still uncracked, what does it mean by uncracked? It means the tensile stress at the bottom is going to be lower than FCR. Again, what is FCR? FCR is going to be a stress limit. It's going to be a value. So for example, we say this FCR is going to be equal to 400 PSI. As long as the stress is going to be lower than 400 PSI here at the bottom, your concrete is going to be homogeneous. It's going to be working tension compression. Once this goes here beyond the 400 PSI, some crack is going to happen, and it's going to be non-homogeneous section, and the rebar is going to get activated. So here's the standard stress distribution. The top is going to be compression. The bottom is going to be tension. For a rectangular section, the stress top and bottoms are going to be equal to each other. The stress here at any point, the stress value, this ordinate, the value here of the stress, is going to be equal to the moment applied at this section. So let's say if you have simply supported beam, look at the point of maximum moment and take the moment from this moment diagram that you just done with in your homework. This Y is going to be the distance from the center or the neutral axis. We call this the neutral axis. This is where the stress is going to be equal to 0 when you start loading. And this Y is going to be the distance to the fibers that you'd like to figure out the stress at compared to or measure from the neutral axis. Maximum y is going to be equal to h over 2. Here we go. This is going to be the maximum y. This is going to be h over 2. The stress value here, this is what we call here sigma c, just named this way. Usually in concrete design, we use the symbol F lowercase. We don't really use sigma. This sigma is taken from mechanics of materials from the previous courses that you have seen. And in this case, the stress is going to be equal to m divided by the moment of inertia of the section multiplied by h over 2, which some cases we call it c, lowercase. If you do integration for this stress block, this triangular shaped block, it's going to give you the force, because the force, as you recall, is going to be equal to some stress value times an area. If the stress is uniform, just one value, you just take the stress times the area, which means the volume of the stress block that you are handling here. So in this case, I'm going to say the area of this triangle times the width is going to give you the volume, and it's going to be here the compression force C. At the bottom, I'm going to have another force that's going to be T. Now, where is this located at? As we went through last time, it's going to be right at the centroid of this triangle, which means at h over 6 from the top. Why h over 6? I simply took here h over 2 divided by 3 is going to be h over 6 measured from the top. It's going to be 1/3 of this triangle base. Now, this compression is going to be the same as a tension, as long as you're still within the cracking point. And this makes sense, because if you do summation of the force, let's say in this direction, the x direction, it has to be equal to 0. So C is going to be equal to T. So let's make this as a given fact that usually tension is going to be the same as the compression. The distance between the two is going to be a factor multiplied by d depth. So this d depth and this j is going to be like a factor, a fraction with a factor that you can figure out later on. We have taken this T section to be like a general section that we can work with. This is taken from an example. So what I did here, I just showed here some dimensions. And then as you see here, you have top stresses, bottom stresses. And certainly you see that the stress on the top is not the same as the stress at the bottom. And this makes sense because you have a T section. There is no symmetry around the neutral axis. The CG location or the centroid location is going to be the same as the neutral axis. This NA stands for neutral axis. If you like to do integration for all the forces here, for this volume of this stress distribution on this T shape, give you a force is going to be equal to C. Same thing, if you do here integration of this stress distribution on this web, is going to be equal to the tension force T. At the end, T needs to be equal to C. And the distance between the two, you can call it Z, or you can call it JD here, doesn't matter. I'm just going to go here with Z. Some people would like to use Y, for example, lowercase. It's okay. There is nothing wrong with that. So let's call it for now Z. Now, how do you figure out the stress? You say the stress is going to be given by this equation. F on the top, at any location here on the top, is going to be equal to what? The moment, applied moment at that section, divided by the moment of inertia, divided by Y top. What is Y top? Distance from the neutral axis to the top fibers. How about Y bottom? Distance from here all the way to there. This is going to be called Y bottom. So M divided by I times Y bottom. Now, how do you do here the moment of inertia? We said that you guys, you have covered this. I'm going to be posting some information. Is going to be end of today. I'm going to put some information how do you figure out this moment of inertia for a rectangular section and for a T section or complex section. If you take this moment of inertia divided by Y top, it's going to give you something called here section modulus, top section modulus, and this is going to be bottom section modulus, which means I divided by Y, which is right here given by this equation. This is the simplest way of looking at this problem, that you say, if you like to find out the cracking point, you say, one, the stress here in the tension side, it just happened tension side to be here at the bottom. One, the stress here is going to be approaching 7.5 square root of F prime C according to the ACI code. This section is going to start to crack. So someone's going to say, what is the cracking moment? I'm going to say it is a limit. It is a moment value. but it's going to be a limit. When the beam section is going to be reaching or approaching this moment value, this beam is going to start to crack. Very similar to the term here, cracking stress. What's the cracking stress? The stress at which the beam at the bottom tension is going to start to crack. Just a value, a limit. So let's say we say 400 psi, which means when the stress here becomes 400 psi and above, beam is going to start to crack. How about cracking moment? I can throw there a number just for sake of discussion. I'm going to say, let's say 20 kip foot. When this beam is going to be reaching 20 kip foot as a moment value, this beam is going to start to crack. Okay. In this example, it says determine the cracking moment. So what is the cracking moment? It is going to be that moment once this beam is going to be approaching, beam is going to start to crack. Information provided here is going to be about the material properties. Right? So I'm going to say, here is the material properties available. I have the steel, yield strength is going to be 6 KSI. Concrete, strength of 4,000 PSI. This is going to be F prime C. The strength at 28 days or specified concrete strength. What does it mean by specified? Specified means this is what I'm asking for, because you can ask for any concrete you wanted. If you're doing an actual design, you can say, I'd like to see here 3,000 PSI concrete, or I'd like to see 4,000 PSI concrete. And they give me here the stress and the strain profile for it. That I don't really need for this type of problems, because the question here is simple, cracking moment. They also give me some rebars and location of the rebars from the bottom. And the beam section, as we call it, 16 by 24 inch deep. Now, my understanding, when I do the analysis for uncracked section means when I'm trying to work here to the cracking point, the rebars is not going to be triggered. They're not taking any tension force yet. Why? Because if you look here at the stress at the bottom, you're not there yet at the cracking stress. So this rebars, it's true that they do some effect. They have some effect. But as long as you are going to be below here, the cracking point, you can just ignore them. So I don't want someone to go and read about it and start to think about, say, you put some material in there and then you say you can ignore it. I'm going to say yes. For the sake of this analysis, this can be ignored because the effect is going to be minor effect. So I don't want to get involved with the rebars at this point. This rebars is going to be really activated or triggered once the entire area here is going to be start to crack, and this rebar is going to be start to take some tension force. I said, okay. The cracking stress, which is a limit, is going to be equal to 7.5 square root of F prime C, 474.3 PSI. Stress distribution for this rectangular section is going to be easy, because what you need to do is to say M divided by S. Where did they get this M divided by S? I'm going to say from here. You see this M divided by S? When you have a rectangular section, this top and bottom, they're going to be the same. It's just going to be one S, because it is, you have the symmetry around the x-axis. I say S is going to be equal to BT squared divided by 6, or H, if you like to use this as an H, this is fine. In mechanics of materials, they usually say BT squared divided by 6. If you like to use it with these symbols, you can say H squared is going to be okay. And the section modulus here is going to be 1624 is the total depth of the beam, squared divided by 6 is going to be that number, 1536. Now, you understand that the stress is going to be equal to mom divided by section modulus. What information you have? Do you have the cracking moment? I'm going to say no. The cracking moment is what required in the problem. I have the cracking stress as a limit. I have the section modulus because I have the section properties, width and depth. So the only unknown here is going to be this M cracking. And M cracking is going to be equal to this number multiplied by that number. Now let's think here about units. The stress here is pound per square inch. And this section modulus is going to be inch cubed. Multiplied by each other is going to be pound inch. I'd like to see this as in kip foot. So this here pound inch. To get it to kip foot, I need to divide this by 1,000 and then divide again by 12 to put it in kip foot. And this is how I came up with this 60.7 kip foot. Any questions?
So Sorry, Professor. So the 60.7 kip foot, that's moment experienced when the section begins to crack?
This is correct.
Okay.
Also, I can reward this, if you don't mind. I'm gonna say, this gonna be the moment if your beam is gonna be experiencing, is gonna start to crack at this limit. Which means if you put 60 kip foot, just 60 kip foot exactly, you're not gonna see cracks. If you put 50, let's say take it from a lower value, right? If you put 40 kip foot, no cracks. 50, no cracks. 60, no cracks. 60.7 is gonna start to crack. And at that point, the rebars is gonna start to take some tension force, effectively. Are we good? Questions?
Can you just say how you converted it to the kips again?
1 kip is equal to 1,000 pounds. So from pound to kip, you just divide by 1,000, right? From inch to foot, you divide by 12. So what you need to do here, I want you to try it quick with your calculator and check and see what value would you get and make sense or not. Can you try, please, and let me know?
60.7. Yeah, I got it.
Great.
Thank you.
No problem.
Professor, you also mentioned that when the moment reaches 60.7, at that point, the rebar begins to experience tension, you said?
Yeah. But we're going to be talking about this next lecture when we start talking about reinforcing section. So what I'm trying to tell you is this. As long as you're going to be below the cracking stress and the cracking moment, this rebar doesn't do you much. Because concrete is still good. It is able to take some tension force and tension stress, if this makes sense to you. Now, once the concrete is going to start to crack, the concrete is not going to be working with you. And the rebar is going to start to take here some good tension force. Okay? This is the simplest way of handling a problem like this. Let me show you another example. We have this normal weight plain concrete. Plain concrete means no reinforcing. So they say you don't have any reinforcing. So if you like to deal with this beam, it's going to be uncracked, because once the beam is going to start to crack, you need to have reinforcing. But it says here plain concrete. The beam is 6 by 12. Yeah, 6 inch by 12 inches. In cross section, as shown in figure 1-4. This gives you the section. The beam is simply supported on a span of 4 feet. Well, 4 feet is very small. This seems to be a test that they are doing here in the lab. So the span is going to be here 4 feet. Subjected to a mid-span concentrated load of 4,500 pounds. And it says, assume here F prime C 3,000 psi. This is going to be the specified concrete. It says here, item A, calculate the maximum concrete tensile stress using the internal couple method. I haven't heard about this yet. Repeat part A using the Flexure Formula approach. Did you guys hear about this Flexure Formula approach? Yes?
Yeah.
Yes.
All right, great. Compare the maximum concrete tensile stress with the value from the models of rupture, FR or FCR, using the ACI recommended value based on F prime C. That's what they're saying. Figure out the stresses in the beam and compare it with the cracking stress. So you'd like to know if this beam is going to be cracked or not under this 4,500 pounds as a concentrated load. Let's move forward and see what happened. Now in this beam here, I need to consider the self weight of the beam. because this beam here is a load, like uniform load on the top of the beam. Concrete unit weight, as we have discussed in the past, it is equal to 150 pounds per cubic foot. So if you like, you should be able to figure out the cross-section area of this beam, which means 6 times 12. And then you'd like to put it here in feet, you divide by 144. So it's going to be 0.5, half a foot times a foot is going to be 0.5 square feet. It's going to be the cross-section area of this section. You take this number, multiply here by 150. As you see here, 150, half of it is going to be 75 pounds per foot. So you're going to have your uniform load as 75 pounds per foot. Now you need to figure out the moment applied to this beam. You have moment coming from two sources. First one is going to be the uniform load, 75 pounds per linear foot. The other one is going to be concentrated load of 4,500 pounds. Moment at the mid-span, maximum moment, is given by this equation. It says here maximum moment is going to be PL over 4 for the concentrated load. And for uniform load, it's going to be W squared divided by 8. So fine. Let me put the values here. P, 4,500. Span, 4 feet divided by 4 plus 75 pounds per foot. 4 feet for the span squared divided by 8. Units here. What I have used here was pounds. And for the distance or the length, I use feet. So at the end, the moment is going to be foot-pound or pound-foot, if you like. It's going to be this value. Now, is this a cracking moment? I'm going to say no. This is applied moment. Based on this given point load and the self-weight of the beam, I have a total of 4,650 pound-foot. Are we good? Hello? Ruth? Yeah? We're good? Questions?
So this is the applied moment, not the cracking moment?
Yeah, where's the cracking? Did I put here any equation for the cracking? I'm gonna say no. I'm gonna go back here to the previous example. This moment here is based on setting the stress to be equal to the cracking stress. So this is a limit. In this problem here, I didn't give you a span, I didn't give you any loads. But in this beam here, I give you the self-weight. You were able to figure this out based on the section. And an assumed 150 pound per cubic foot self-weight. And an external applied force of 4,500 pounds right at the mid-span. Based on this two piece of information, I was able to figure out the applied moment to the beam. This is how much the beam is gonna see. And this is like your homework 1. You're given some loads and you're trying to find out the applied moment. Let's look here for the stresses. How can we do the stresses? And what can we do with this force, tension and compression? If this is 6-inch and you'd like to do here some integration for this, where this point load is going to be at for this compression. As I said, it's going to be at 1/3 of this triangle base. So if this is 6-inch, this is going to be at 2 inches, right? Same thing for the bottom tension force. If this is here 6-inch, 1/3 of this triangle is going to be at 2 inches from the bottom. If I have total of 12-inch, subtract 2 and 2, you'll end up with the distance between the two forces over 8 inches. Are you good about this figure?
Yes.
Okay, good. When I see here two forces opposite to each other and equal to each other, we call this a couple, right? Moment developed from this couple is equal to C or T multiplied by Z. Yeah, I've taken this in statics. And this moment should be equal to the applied moment. We call this internal moment. We call this external applied moment. So if I looked here, the moment that you have done in your homework was external applied moment. Due to what? Due to loads. It's going to be PL over 4 plus W squared over 8. But the moment that I'm talking about here is going to be internal moment. Why internal? Because it's going to be based on internal forces. This C and T is going to be internal forces within the beam itself. These forces, we call this external forces, right? This self-weight and the applied point load, these are all external forces. But this moment that I'm talking about here, C or T times Z, is going to be an internal moment. Okay, listen to this. As long as this beam is stable. What does it mean by stable? Which means it's not falling apart. The external moment has to be exactly equal to the internal moment. Which means this external moment that I've just calculated out, the 4650, is going to be equal to 8 times C or T. Which means 8C is going to be equal to 4650. So what do you do with this? You can figure out C or T. Does it make sense?
Yes.
Yes.
All right, very good. So as it says here, there's some description here and discussion that you can go through, which is exactly what I was talking about. This external applied moment is going to be equal to C times Z or T times Z, one of them. Both is the same because C is going to be equal to T. Look at the moment value, 4650, external applied moment. And we decide here to multiply by 12. Why? Because this moment is going to be pound foot, and this Z value is going to be in inches. So I need to convert this moment from pound foot into pound inch. You have 12 inches in a foot. So what you need to do, multiply this value, this moment here, by 12 inches for conversion. And it says it's going to be equal to C times Z. Now your Z is going to be equal to 8 inches. Someone's going to say, where are those values? Going to take you back. 4650, external applied moment, and Z is going to be equal to 8 inches. With that, I'm able to figure out the C. The compression is going to be this value, or the tension force. Both of them is going to be equal. Are you good? So with that, I was able to figure out the force. How's that? I said external moment is going to be the same as the internal moment. External moment is going to be given here, just calculate out. Internal moment is going to be C or T multiplied by Z. So I'm good. I was able to figure out the tension force or compression force. I'm going to take you back one slide just to read what is needed here. It says calculate the maximum concrete tensile stress using the internal couple method. Internal couple method, right? Let me move you forward here. Internal, we said that's going to be internal forces, right? Couple, we said that this is going to be a couple. So after you figure out the force, how would you find out the stress? I'm going to say, let me take you here back when I was discussing doing the integration, which means the volume of this. The volume of this stress block is going to be equal to that force. So how much is the volume of this stress block? It's going to be equal to F top times 6 inches times the width of the beam. It's going to be divided by 2. It's going to be equal to C. Same thing for the tension. So let me move forward, see what's going to happen. For F top, it says here is going to be equal to 388, which is the same as F bottom. But now I want you to consider looking at this. I'm going to go back here a few slides and look at this slide, which makes sense. Look at this slide here. F top and bottom is going to be the same. The compression force somewhere between 6 kips to 7 kips. The depth here, this depth is going to be 6 inches. And this width was given to me. How much was the depth? The width? The width was equal to 6 inches. And the total depth was equal to 12 inches in our example. If I take this number here, I'm going to say 6 times 6 divided by 2 is going to be equal to that area here times the stress. It's going to get me the volume of this block. So how, again, the volume of this block is done? Take the stress, it's going to be your unknown, times 6 inches, divided by 2 is going to be the area of this triangle. Multiply by 6 inches is going to be the volume. He said this equal to the compression force. It's exactly what we have done here. Total compression force or total tension force, we have solved for it. We say total compression force is going to be equal to 69.75. How this is done? By setting external moment to be the same as the internal momentum value. Here's the external moment times 12 for conversion is going to be equal to C times 8. With that, you have the compression force or the tension force. This compression force is going to be equal to the volume of the stress block. Now, where's the volume of the stress block? You can say, okay, let's do it. It's going to be 1/2 of F top. Why 1/2? Because you have this triangular distribution times 6 inches for the width and 6 inches for the depth of this triangular distribution. It's going to be equal to what? To the tension or compression force. With that, you should be able to figure out the stress, F top. F top is going to be 388, which is the same as F bottom. Why? Because you have symmetrical section about the x-axis. So I was able to find out here that the stress equals 388 psi top or bottom. Any questions? A chance to ask questions. Before I ask. All right, so this method that I have used here, this is what we call it. We call this internal couple method. And with that, I was able to find out the tensile stresses within the beam. So good. I'm gonna jump here to item C. I'd like to see here the stresses with the ACI and compare it with this, and then go back here to item B. So, okay. Let's look here at C. 7.5 square root of F prime C. What is this lambda? Anyone recall the lambda factor? Lambda factor. This is the effect of lightweight concrete. If this is going to be normal weight concrete, we take it equals 1 times square root of 3,000 psi. I have 411 psi. Now, has this beam cracked yet? Let's give you the question to you. Yes?
No.
Is this beam cracked?
No.
No. Why? Because the actual stress that you have in there for this given loads is going to be 388. For this beam to crack is going to be at 411 psi. So it is not at the cracking point yet. Some good news that this beam is still in good shape. You can say, how about this Flexure Formula approach? You can say Flexure Formula approach. This is the same one I have used in the first example. This is going to be, that was the simplest way of doing it. You just say here, you set the stress to be equal to M divided by S, or M divided by I times C. So I'm going here to item B to use the Flexure Formula approach. What's the Flexure Formula approach? This is the one that says the stress is going to be equal to moment divided by moment of inertia times C, which is the depth. Distance. Where do I have this method? If you guys recall this, I'm going to take you back and say, yeah, it's going to be the same equation that you used here. We call the Flexure Formula. This is the way it's called here in this book. So moment of inertia, BH cubed divided by 12. Width is going to be 6 inch. Total depth 12 inches divided by 12 is going to be 864 inches of ore. So all units here I'm going to be using is going to be inch and pound. The stress here is going to be M times C divided by I. We're going to set it to how much? We're going to say here's the moment, applied external moment, 4650. What units did we use here for this 4650? That was pound. Was it pound inch or pound foot?
Pound foot.
Pound foot. So I need to convert to pound inch because everything is going to be in inches. So I'm going to multiply here by 12 inch. Now this is going to be the moment. Maximum neutral axis depth that I can go to is going to be 6 inches. What is that? This is going to be the maximum distance from here to there. It's going to be 6 inches. Or to the bottom is going to be also 6 inches. This is going to be the maximum Y, which is, or maximum, which is C. Moment of inertia just calculated out is going to be 864. Around this number is going to be exactly 388, very similar to the other method. So whether that you do it with the Flexure Formula approach or you do it with the couple, internal couple forces or method, you're going to be getting exactly the same answer. Whether you do it this way or that way is going to be 388. Again, the comparison with the 411 is going to tell you here that you still have some room for this beam to take some loads without cracking. So this beam is uncracked yet. Any questions? Yes? We're good?
Yes, we're good.
All right, thank you. All right. One more example. It's going to get a little bit more complex. This is a T section that you guys were looking at that I put in the beginning slides. Now we have a T section. It says here the concrete is going to be 4,000 psi. There is no reinforcing. And this says here, assume positive moment. What does it mean by positive moment? Means compression top, tension is getting the bottom. And then it says here, use the internal couple method and check using Flexure Formula. I guess we know what is the internal couple method and we know what is the Flexure Formula. Either that you figure out tension compression or you just do M divided by I times Y or times C. When you look at this problem here, no one's going to give you all of these numbers. So for example, this number is given to you, the width. This depth of the flange or thickness of the flange is going to be given to you. This 20 inches given to you. These numbers here, they're not going to be given to you. And this distance here, not given to you. You need to figure this out yourself. But because this is an example, I had the chance here to have all the values for dimension that I'm looking for. I said, first, I'm looking for location of the neutral axis, the centroid. I said, okay, how do you do this? Here's the equation. Do you take the moment here about some axis? So the sum axis, it says summation of A times Y divided by summation of A. What does it mean by that? It means here that I have two sections. This is going to be A1, let's say, and this is going to be A2. How much is A1? You can say A1 is going to be for this section here. It's going to be 20 times 4. How about A2? 20 times 5. Do we have that? You can say yes. Look at this. 20 times 4, 20 times 5. This is going to be A1. This is going to be A2. I understand here, Mom. Total area is going to be equal to 4 times 20 plus 5 times 20. I'm going to go back here one step. 20 times 4 plus 20 times 5. Total area. We are taking here the moment about some axis here. Look at this RA. We are taking the moment about this line. So put a line here, draw a line here, start to hit the moment of each one of these areas. Now, where's the first area? We say first area is given the top. How much is it? You see 80, 20 times 4. And the moment arm to this axis, I'm going to say is going to be equal to 24 minus 2, correct? Why? Because this area is going to be concentrated right here in the top flange at 2 inches from the top. So distance from the bottom, from this axis at which we are taking the moment about, to this centroid of section number A1 is going to be equal to 22 inches. Any questions on this? We're good?
Good.
You're good. All right. Thank you. How about for the second area? I'm going to say second area. Where is centroid of the second area? I'm going to say second area, centroid is going to be at 10 inches from the bottom. Why? Because you have total of 20, it's going to be 10 inches. My equation is going to look like this. Take the moment of each one of these areas about this bottom axis and then just add them to each other. I'm going to say I have here 80 times 22 plus 100 times 10. Let me go there. 80, here's the first area, times 22, plus 100, the second area, times 10. And you divided this by the total area. So you get here 1533 for the location of the neutral axis. So I guess in this example here, this is exactly what you're looking for. This is what you wanted from the previous class. Mechanics of materials or statics. You do summation of the areas about some axis here at the bottom, And then you divide this by the total area. We give you the neutral axis location or centroid of the T section, entire T section. This says it's going to be 15.33. So this Y bar is going to be location of the centroid of the combined section. Yes, Alexis, you have a question?
You answered it actually right now. Thank you.
Good. All right, thank you. So right now, this is going to be the centroid, which also is the location of the neutral axis. So right at the centroid, you have no stresses. This is what we have studied back in mechanics of materials. Right at the centroid, as long as you just have a moment, like flexure forces, there's no stresses at this point. So, okay, good. Now, what should I do? I'm going to say now, what should I do? I should be able to find out the stresses top and bottom if I want to. But before I do this, I need the moment of inertia. This is going to be one way of thinking about this. So, okay. Or, if I have the moment here, total applied moment, well, there's no total applied moment. Internal moment that I have there, I can figure this out also. Let me see what's happening here. Let's say the stress is here, top and bottom. How will you find out the stress is top and bottom? And what is the cracking point? They give me here the concrete strength to be 4,000 psi. Normal weight concrete. Look at this. Lambda equals 1 for normal weight concrete. Take this normal weight concrete 1 times 7.5 square root of 4,000 psi. With that, you have a stress for cracking is going to be equal to 474 at the bottom. Meaning, this is going to be the limit. When the stress here at the bottom is going to be reaching 474, this beam is going to crack. Okay? So good. So once the stress here at the bottom is going to be 474, how much the stress is given in the top? I'm not trying here to ask you to do the formula, which is m divided by I times y or times c. I'm not asking for this. I'm simply asking if you have this symmetry between the two triangles and you know location of the neutral axis to be at 15.33. And if I tell you here that the stress at one point is going to be 474, how much is the stress at the bottom, in the top? Well, what you can say here, 474 divided by 15.33 is going to be equal to the stress on the top divided by the distance from here to there, which is 24 minus 15.33.
Are we using similar triangles to solve?
Yes, just from symmetry, which means that we have, when we have here two similar triangles, you can say the stress at the bottom divided by stress on the top, correct? Is going to be equal to this depth from here to there, depth of neutral axis from the bottom, divided by depth of neutral axis from the top. So you can do it more than one way. You say stress divided by the stress is going to be equal to this distance divided by this distance, or you say F bottom divided by this depth is going to be equal to F top divided by this depth. So this is exactly what we have there. If you take 8.67 divided by 15.33, what is that? It's going to be this depth divided by this depth by ratio. So this depth to this depth ratio multiplied by this F at the bottom is going to get you here the stress on the top. It turned to be 268 psi. So when the stress at the bottom is going to be 268, excuse me, the stress on the top is going to be 268, at the bottom is going to be right at the cracking point 474. Very good? Yes? Finding out the stress on the top based on the stress at the bottom?
Yep.
Okay. This has nothing to do with my equation. The stress is going to be m over I times c. No, it is not related to this. It is when you set the stress at the bottom to be 474, like at the cracking stress. How much stress do you expect here? Once you do this, you're going to say, okay, good. Now, if this is going to be 474, can I find out this tension force? Say yes. Tension force is going to be equal to 474 times 15.33 divided by 2 times the width 5 inches. I'm trying to find out the volume here. of the stress block on this. Let me show you this picture. The bottom was a very simple triangle. We come to the tension side. It's gonna be like one of these, but you just put at the bottom, which is very similar to the second example that we have done today. You have the stress top and bottom, you can do tension compression. Let me show you also the calculation of that force. Here's F on the top. So location of this tension force was simple for me. I should be able to do it easily. 1/3 of 15.33 or 2/3 of 15.33 is gonna be 10.22. Why? For this triangular shape, 1/3 from the bottom or 2/3 from the neutral axis. 2/3 of the neutral axis is gonna be 10.22. How is that? Take this 15.33 times 2/3, give you this location. My problem here is trying to find out the compression force C. Just say, well, C is going to be equal to T. I understand that. The question is, what is the location of this force from here? I understand T is going to be simple. It's going to be equal to the 474, the stress, times 1533, times 5, divided by 2. It's going to be the stress block value. With that, I have tension compression. The tension force location, I know is going to be at 2/3 from the neutral axis to the centroid of this triangular shape. It's going to be 10.22. How is that? 1533 times 2/3. Now, my problem is going to be location of the force C from the neutral axis. I cannot say it's going to be at 2/3 from this because this stress is not applied on a rectangular shape. It is applied on a T shape. So here you have more material, more meat than in this little web. Which means actually in reality, this C, if I'd like to analyze it, I need to consider it to be 3 forces. This is why I'm gonna jump here to this slide. I want you here to imagine what's happening. Push this stress block right back here. Just push it, slide it down here. And slide the whole thing and put it here on the top. It's gonna give you this triangular distribution stress on this T shape. So this stress is gonna be the same as this stress because if you slide this, put this on the top, they need to be of the same height exactly. Now also slide this back. This is gonna give you here one triangular distribution. Are you good about this or not really?
Just the last triangle. I think it was C1. That's the part I didn't understand how it all connected.
All right.
Or C2. So I see how C1 applies and then C3, but not C2.
Let me push this here so that we know what we're talking about. So imagine if I have here this triangular distribution. So I'm going to be drawing this line here. And from here, it's going to be a straight line like this. I'm going to be doing it this way. From here, I'm going to be doing it with the same slope. Same slope. You know what? See my screen, right?
Yes.
Very good. I'm gonna say, here's the stress distribution. From here, it's gonna be like this, a straight line, a straight line. Stress block is gonna be like this, right? I'm gonna be drawing this, the stress block here. And here's gonna be coming like this. Let me just draw it differently. Enlarge this a little bit. Now, don't look here at C1 and C2 and C3. It's gonna be the stress on the top fibers. All right. I'm gonna be connecting this to the stress right here. So what you're gonna see here, the stress is gonna look like this. This is gonna be horizontal, and this is gonna be doing this. This makes sense?
Oh, okay. Oh, okay. Now I see it.
So what's gonna happen here, the stress is composed of 3 sections. The first section is gonna be this guy, which goes to the web when I push it back to the web. Right above it, and also it has the same width, is gonna be this guy here. So if you like to look here at the stress block from the side, if I'd like to look from it this way, right? You're gonna see here the stress block is gonna be like here. Here's the T. Let's see, here's the beam is gonna be like this. This is gonna be the T. And here's the stress distribution. So at the beginning, this is gonna be this piece. This piece is what we call here C2. And this one here, let me change the pen. This one here is gonna be this block, C1. And this one here is gonna be C2. And this one here is gonna be C3, the bottom.
Roger that. Thank you.
Let me redraw it here.
So essentially, you're just breaking up the compression parts into shapes that you already know, right?
Yeah. So I'd like to divide it. So let's say that I'm looking again from this side, right? So from this side, here's the beam section. And the T is gonna be about here. Neutral axis is gonna be here. This distribution is gonna be like this. So I need to divide this because this section here is gonna be applied to this T section. So I need to divide this. I'm gonna be taking this little section, this distribution, I'm gonna put here compression force for it. This is gonna be on the web because it's gonna be applied on this little piece. And this is what I'm gonna be calling here C3. In the top, this is now trapezoidal applied on the flange. So it's gonna be kind of a little bit of trouble. So I'm gonna divide it into 2 sections. One of them is gonna be a rectangular section, which I'm gonna be calling here C1. And then I have C2, it's gonna be right at the CG of this little triangle. So now location of this force from the neutral axis, this is here is gonna be 2/3 of this little depth from here to there. And location of this C1 is gonna be from the center of the flange to here. Location of C2, which is right at this triangle on the flange, is gonna be 2/3 of this triangular base plus this little section. If this makes sense to you there. Should I redraw this differently and talk about it, or what do you guys think?
Yeah, can you redraw it?
Okay, give me a sec. Just clean it. You guys see my screen now?
Yeah.
Okay, good. So I'm gonna say stress distribution, if I cut the section and look from this side, is gonna be like this. The T is giving the top, the flange, which means this piece is gonna be from here to there. Neutral axis is gonna be the distance from here to there. So it's gonna be here. Now, this is going to be triangular distribution applied on a T section. So I'm going to divide this into 3 areas. Yes, okay. On the flange is going to be this top trapezoidal distribution, and on the web is going to be this triangular distribution. Okay. Let me use different color. I'm going to say, since you're going to be dividing it, it's going to be tough to work with this trapezoidal. Especially that the problem here usually with trapezoidal, how to find out the centroid of it. So I'm going to say, you know what? Let me divide this into 2 areas. One area is going to be the rectangular shape. One area is going to be this triangular shape on the flange only. And the third one is going to be this triangular shape on the web, which means right here. What do you call this one? This one is going to be C3. Where is this C1? You see, this is going to be C1, which means this guy. Where is C2? It's going to be this guy here. You're good? Yes?
Yes, I see it better now.
Okay, good. So now I need to put 3 forces. And where's the first force? C1. Where is it going to be at? It's going to be right in the middle here. It's going to be C1. Now, where is your C2? You say C2 is going to be for this triangular shape. It's going to be right here. Where is C3? It's going to be right here. So number 1, I'm going to be taking this compression force divided into 3 forces. C1, C2, and C3. Second thing that I need to do is to find out the location of these forces from the neutral axis. Correct? I need to do this. Because finding just the force is not enough. I need also distance. So distance is not going to be that tough. Why? Because I have the height of this triangle. I can divide this by 3. And this is going to be 2/3 of the triangular base. This C1 is going to be right in the middle of the flange. Why? Because this goes here to this rectangular shape. How about C2? I'm going to say C2 is going to be at 1/3 of the flange thickness from the top. Because this is going to be like triangular shape. It's going to be 1/3 of the flange depth from the top. Are we good? Yes? All right, let me go back here. So again, I have here 3 forces, C1, C2, and C3. So fine. Let me go back here and look at the analysis that we are doing. Now the tension force is simple to calculate. It's going to be equal to the stress at the bottom times 5 inches times 1533, divide this by 2 to get you the volume. So I have it here. Here's the tension force. 1/2, because this triangular shape, 474 is going to be the stress at the bottom, times 1533 depth of the web, times 5 inches for the width. You have here 18.17 kips. So this is easy, right? I said, how about the location of the force? As I said, it's going to be 2/3 from the neutral axis. Let me take you back one step. I said, this depth here is going to be equal to 2/3 of the total depth of this triangular shape. So if you take 1533 times 2/3, it's going to get you here 1022. This is exactly what I have here, 1022, 2/3 of 1533. This is good. Now this force here is going to be in tension. How about in compression? I said I'm going to have here 3 forces, C1, C2, and C3. Okay, let me find out each force. How do you do here C1? C1, if you look here at the stress on the top, the stress on the top, as we said, that was equal to 268. I said, okay, let me take you here to this slide. If the stress here is going to be 268, can you figure out the stress at the bottom of the flange? Just hypothetical here question. Is it possible? Is there a way? Yes or no?
Can you use similar triangles?
Exactly. So how do you do it? This is going to be 268 divided by total depth from here to there, which is 8.67, correct? Multiply this by 4.67. That's it. So the stress right at this point with these two similar triangles is easy that you should be able to do. And with that, you're going to find here the stress at this point here, at the bottom of the flange, is going to be 0.1444. Is it okay? And the stress on the top is how much? 268. You subtract 144, you end up with 0.1236. You can simply say, if I add this to that, it's going to get you here the total stress. Because look at this, slide this back and slide this back. Total stress on the top is going to be equal to this plus that. In the block that I did here and I was trying to work with, total stress here, total stress that you see here is going to be composed of two stresses. This is going to be one value and this is going to be another value. This stress is going to be the stress at the bottom flange. This stress, total stress, give you the stress on the top of the flange. Total stress, 268. And the stress here, you're able to find it, 0.144. This stress value for this little triangle is going to be equal to 268 subtracting 0.144. That's exactly what we have done here. And with that, we have the stress 0.144, 0.123, you add it to it, it's going to be 0.268 K sign. You're going to say, okay, let me go here back one step. You have the stress here at the bottom of the flange, this for C1, times 20, the width, times 4 inches. Does this make sense? Yeah. It's going to be 20 inches for the width, 4 inches for the thickness, and the stress is going to be 0.144. How about the stress here? You say, yeah, this is simple. Let me just look at this picture and try to think about what stress value they have here, or what force value. It's going to be 0.1236 times 4 inches for the flange thickness, divide by 2, get you this area here, times 20 inches. So this is going to be C2. Let me check. 1/2 the stress times 20 times 4. So good. How about the stress here, C3? I said, well, this is here 4.67 for the depth. And this is stress 0.144. So I'm going to say 0.144 times 4.67. Now, divided this by 2 times the width of the web, which is 5 inches. So let me look at this. It's 5 inches, 467 for the depth of it, times the stress, divide this by 2. Now I have 3 forces. Total, you just add them together, is going to be 18.18, which is exactly or very similar to this. It just depends on the approximation that you do in your analysis and rounding up the numbers or rounding it off. So here we're able to prove that tension is going to be the same as the compression. I said, well, is this enough? Now, where's the moment? Because let me take you back here to this slide. It says, calculate the cracking moment. Based on what? Based on the internal couple method. So I need here the moment. Now, how do you do the moment? If you want to do the moment, you need to find out here this Z. What is Z? Let me take you back. Z is going to be distance from tension to compression. Now, instead of one compression force, now I have 3 compression forces. I have this compression force, C1, C2, and C3. So in this case, I need to have Z1, Z2, and Z3. So let me borrow this for a second. Let me see, what do we have in here? Here's the flange. The flange is going to be in here. This is here is going to be C1. This is here for this triangular shape is going to be C2. For the web force is going to be C3. Now where's Z1? Z1 is going to be going to here. From here, not from here, excuse me. It's going to be from here to here. This is here is going to be Z1. And Z2 is going to be this one to that point, to the force C2. Z3 is going to be this one, Z3. Now how much is the moment? Total moment is going to be equal to C1 times Z1 plus C2 times Z2 plus C3 times C3. So I need to find out this Z distance. Now this is going to be a geometrical problem that you should be able to solve it. And then at the end, this is going to be your total moment. is going to be Z1 times C1 plus Z2 times C2 plus Z3 times C3. It's going to be right here. I guess I'm going to stop here at this point, and next time we're going to be doing refresh for this one. I'm going to be going quickly through it, and then we take it from there. If you have any questions, stay around. Otherwise, please sign out, type your name in the chat room, and go. You can leave if you want to.
All right, thanks, Professor.
Right, you guys have a good night.
Professor, is the second homework due next week?
Yeah. Did you see it?
Okay. I'm not sure. Thank you.